what's going on each day, so you need to make sure you're checking Canvas, especially if I'm gone, make sure you're checking Canvas. Today what we're doing is we're going over acid-base. We won't get to buffers, but we'll get to pH, pOH, and all that stuff. I've put up the solubility rules. We'll talk about that during lecture. I've put up 5th period because they're a little off from everybody else, and then I'll put up 7th and 8th period so that it'll be your guys's. We picked up as we came in a titration of beverages. We're going to do that next time. And if we scroll down here, you'll notice that I put for the 15th, which so Tuesday is the lab. Thursday will be finish the lecture of acid base, and then we'll do the pre-lab buffer. Lab notebooks are due this day, and then we'll come back 1st to 4th term to the buffer lab, and then the 22nd will be a work day. And then your test is from the 21st through the 28th is when it's open, yes. No, the buffer lab will not be in the notebook for me to correct the notebooks for 3rd term. Okay? You'll get the pre-lab or you'll get the buffer lab as you turn in your other lab notebook. If you want to put it in before you turn it in, that's fine. I just need their lab notebook with the 3 labs, which will be your pH home lab, your titration lab from last time, and your beverage lab titration. Yes?
So if we're not here for the buffers lab, is it easier, or like, should we just come after school?
So if you're not here for that buffers lab, you need to come during tutorial on the Wednesday, because we're going to start taking it down on the Wednesday. Okay? All right, so let's look at that lab for a minute. I want to look at that lab and talk to you about it. I think it's right here. Let's scroll up to the top. So this acidity of beverages that we're doing next time, we're actually going to test apple juice, grape juice, and pineapple juice for how much acid they have in them. Pineapple juice will have citric acid, grape juice will have tartric acid, and apple juice will have malic acid. And we'll be titrating each of those. Now, when we do the titration, we're going to do a quick one for each of them. And right after the quick one, we're going to do a long one with a pH probe. Okay, so you're going to need to print that one out. So as one person in the back comes back into the classroom to print it from the computers, the other one can do the quick titration for the next juice. Okay, and get it set up so when the person has printed the graph from the first one, they can go back and set it up and do the second one. Then I want the next person to come in and do it while the other one that was in here first does a quick titration and sets up the next one for the last juice. Okay? So what we're doing besides that day is we're going to be, you've got a pre-lab, of course, that you get to do. And then we've got an example of some titration curves. And you've got a procedure A. We're actually going to be testing different kinds of indicators and see when they change color. So you're going to label test tubes 1 through 5. You're going to write down in the data what your indicators you're testing. You're going to use a 10 milliliter graduated cylinder, measure to pour 2 milliliters of acetic acid into each test tube, and add 1 to 2 drops of each indicator into each of the test tubes. Once you've done that, you're going to observe the initial color, okay? And you're going to rinse the graduated cylinders with distilled water. In another graduated cylinder, so you're going to use 2 graduated cylinders, you're going to add 3 milliliters of sodium hydroxide. And then you're going to add the NaOH to each test tube at a time, 1 milliliter, and record the change. So you'll have several different indicators that you're testing, but you're adding, so nothing at first, then you'll add 1 milliliter to each of them, record a change. Another milliliter to each of them, record a change. And you're going to do that until you've used all of the 3 milliliters of NaOH. Then you're going to rinse out the tubes and you're going on to your titrations. Now, you'll notice that there is no procedure for the titrations. You've done a quick titration, you've done a pH probe titration. I want you to write the procedure for this. Okay? So you need to write this before you come next time, and then you have to have a clearance stamp before you go back in lab. So you got to have the pre-lab done and your procedure done by next time. Okay? I've given you a table for your indicators. We won't test more than 5. I've also given you a table for your procedure B. You can put in there whatever you want. I just made you a table and you can use it however you need to. After you finish with that, you do have an analyze the results and your conclusion, and that needs to be finished by Thursday next week and turned in. Okay? So we'll do the lab on Tuesday, and it will need to be finished by Thursday. So we're going to go back to our notes, and we're going to take a whole bunch of notes today. Then next time we'll do a lab, and the time after that we'll do notes, and the time after that we'll do a lab, and then we'll do notes, and then we'll go from there.
So so the test that's coming on the 21st. After that, that's when you're going to be on.
Yes.
And then that's just going to be nuclear.
Nuclear, and then you'll start organic if I don't make it back. But I'll have all of those lectures recorded.
Would you say organics kind of as close to nuclear easiness-wise?
It depends. It's more of a non-math side brain.
Yeah, that's what Max said.
Okay. Yep. I do. His name is Mr. Robson. Yes, he just finished a class of chemistry at the college, and he's going to be a physics teacher.
Where are you?
To have surgery on my neck. So, yeah. Okay, so let's go forward. I'll be gone 4 days before spring break and 6 days after if everything goes well. So, so hopefully you'll be good. But all of my lectures will be up online, so you can access them there. So if he has trouble with accessing on the thumb drive, no, he'll be able to help you though if you need help.
So what are we doing?
So you're going to do nuclear chemistry, and you'll start into organic chemistry if I don't make it back.
Where are we watching?
Uh-huh.
Oh, okay.
Okay, so let's start with this. Water can self-ionize. We do need to book a little bit fast on this. So this is starting at 9.4, I believe, in your notes. It's right after the first 7 notes that we took at the very front. You need to write a neutralization reaction. Basically, is when you have the same amount of hydroxide as you have hydrogen ions or hydronium ions. This right here is a Lewis dot for the self-ionization of water. This side is the conjugate, of course. So conjugate acid, conjugate base. And they've color-coded it, so this base goes with this acid, and this base goes with this acid. So those are your conjugate pairs. You'll notice that they've also helped you by coloring one water red and the other water blue. So you can see that the red water gives off a hydrogen to the blue water. Okay? What type of reaction is this? What theory does this go under? There were 3 theories. There were Lewis, Bronsted-Lowry, which they'll call Bronsted, and Arrhenius. Which one did this go under? Lewis made one product, so this wouldn't be Lewis because it has 2 products.
Oh, so Lewis is the one where it's 2 combined to 1.
Right. Arrhenius would give you salt and water, and we're not getting salt and water, so it has to be Bronsted-Lowry. Bronsted-Lowry, and I remember this because Bronsted-Lowry, there's 2 people, and they're going to have 2 different charges. Okay? Arrhenius, you're going to get salt and water. Lewis, you're going to get one thing. Okay, so this is your Lewis dot, so it sort of shows what's going on. We're going to go forward here. We're going to talk a little bit more about that equation. This is not the Lewis dot of that equation, but it's the same thing. If we were to write the K for this equation, remember K's can only have gas and AQ in them. So I would cancel out the liquids on this side, and since it's products over reactants, it would just be worried about the K, the concentration of hydrogen or hydronium ion and hydroxide ion, and we get this reaction right here. Excuse me. The hydronium ion and the hydroxide ion are the same at neutral. So at neutral, we have 10 to the minus 7 molar of both the hydronium ion and the hydroxide ion present in distilled water. Because it's the same amount, it's neither acid or base, it's neutral. So this reaction right here, we're going to be using a lot, so make sure that you've got it written down on your paper because we're going to be using it in the next couple slides. When we talk about an acid solution, I have more concentration of acid than I do of base. So I have more H3O plus then I have OH minus. In a base solution, I have more base, or OH minus, than I do H plus, H3O plus. So as I'm talking about the different solutions, I'm talking about the concentration of each that I have in there. Yes?
How is OH the base consistent base the one receiving?
Base is,
Just have less hydrogen.
right, so it will be the one receiving a hydrogen.
When it does go.
Right.
Okay. I thought it started out H2O, H2O.
It did, it self-ionizes, but if you're going backwards, then the OH minus would be the base, right?
It would be the conjugate.
Right. Okay, so how much I have left? All right, so let's take this equation down here at the bottom, where we have H3O plus and OH minus equals negative 14, and try some problems with it. So on the top here, we would take, and since you have one of them and you want the other one, remember Kw equals concentration of hydronium, that's a plus 3 by, 3 by the way, and hydroxide equals to 10 to the minus 14. And that's molar, of course. And all these would be molar. I just left off the m. So up here we would take 10 to the minus 14, and we would divide it by parentheses 1.0 times 10 to the minus 7. That would give us the concentration of hydronium ion. Okay, so let's go ahead and do that. What will we get? Those that are math whizzes know really quickly, all we have to do is add or subtract the exponent. So we should end up with 10 to the minus 7, right? Because negative 14 minus a minus 7 is 7. Now, the next one is not as easy because we've got a number in front. That works real well when that number in front is 1, but when it's not, we actually have to put it into our calculator. So here's 10 to the minus 14 divided by 3.8 times 10 to the minus 2. Let's see what the hydronium concentration would be for this one. So if you need a calculator, there's a whole bunch in the sink. You're welcome to use them. But we are going to be using calculators a lot today, so go ahead and get them out.
So now you want to show that?
Yep. So that top one is 10 to the minus 14. It sort of got mushed there a little bit.
So in your calculator, how would you think that?
10 to the minus 14 divided by parentheses 3.8 times 10 to the negative 2, close parentheses. The caret button's on the left on my solar ones. It's the X with a box.
Yeah, I
Okay.
find it. It's usually like that.
Yeah, it's just the X with a box up. Okay, anybody got the answer there? Say it one more time. Okay, and that would be molar. Okay, did everybody else get that one? Okay. All right, I'm going to let you do numbers 3 through 6, and I'm going to randomly pick people to put it up on the board. So go ahead and get started, and I'll give you who's putting it up on the board in just a minute. Okay, let's have Tasha, go ahead and put up number 3. Megan, go ahead and put up number 4. Callie, go ahead and put up number 5. And Juliana, go ahead and put up number 6. I just have one other person doing number 5 who's missing doing their duty. Did I not call somebody? Thought I did. Juliana, is that you on 5 or did you do 6? Okay. Okay. Thank you, Taylor. Okay, let's go ahead and check them. On number 3, if you agree with what's up there, thumbs up. What does it say? 2.63 times 10, oh, sorry, 1.053 times 10 to the minus 6. Okay, if you agree with number 4, 1.75 times 10 to the minus 19 for number 4. That's right, it's not right. Why would it not be right? Because both of the exponents have to add up basically to negative 14. It doesn't. So let's take that really quick. What did we get? Those of you that didn't get that. So 1.75 times 10 to the negative 11. Okay, this is one of the things that I find that I do wrong with this. I forget to put the parentheses around that whole bottom number. If you don't do that, it changes what's going on there. Okay, so number 5, do we agree with that? Up or down? That was actually good. Should be good. And number 6, up or down? Thumbs up, you got it. Thumbs down, you didn't. Number 6. I got 1 thumbs down and 1 thumbs up. What's about the rest of you? Thumbs down, thumbs up. Ooh, okay, let's check this one really quick. We got it. We're all over the place. So 10 to the minus 14 divided by parentheses 8.1 times 10 to the negative 6. Bring everything down. I got 1.23 times 10 to the minus 9. Is that what everybody else got? 1.23 times 10 to the minus 9. Okay, so we had some issues there. And I'm not sure exactly how to change those calculators in the scientific notation. Yeah. So we probably need to worry about that on those. Okay, so let's go forward. We're going to be using this equation again right here. Now we've got the hydronium concentration. I want you to find the hydroxide concentration. Again, I'm going to pick people to put it up. Yes. Same equation, 10 to the minus 14 divided by what you're given up there. Make sure it's in parentheses. Okay, let's get some people up there. Honor, would you take number 1? Kira, do number 2. Aubrey, do number 3. Grant, 3. And Carlson, 4. Okay, let's go through each one of these and see how well we did. Number 1, thumbs up or thumbs down? Oh, awesome, thumbs up. Okay, number 2, thumbs up or thumbs down? Good, another thumbs up. Number 3? Good. Number 4? Awesome. So we're all on the same page. Now remember, a lot of you did not do significant figures. This only has 2 numbers, so we should only report 2. This only has 2 significant figures, we should only report 2. This only has 2, we should only report 2. So we got a little bit of calculator throw up going on, so don't do that. Okay, let's go on to the next one. Whoops. Next one we're talking about, I don't know why that it does this. Okay, we'll go back. It doesn't want, it just wants to keep it. Okay, so we'll try and erase this. All right. Whoa, got a little angry there, yeah. All right, so pH is basically a power for hydrogen. And it is an easy way for us to tell if it's acid or a base. With a pH of 7, we have a neutral solution. If the pH is less than 7, we have an acidic solution. If the pH is greater than 7, then we have an alkaline solution. You'll notice that your pH scale that I gave you for your home lab and the one here up on the board goes from 0 to 14. However, if you have a really strong acid or a really strong base, you can actually get a negative pH, and you can actually get a pH up to 16, depending on the strength of the base. So it does extend a little past those each way, depending on how strong it is. The hydrochloric acid that I get that's 12 molar will read about a negative 1.5. The sulfuric acid that's an 18 molar reads down around there too. So they do extend out a little bit, but for the general population of stuff that we work with, it's 0 to 14. So to give you some ideas, if you have not started your lab, your home lab, there's some things here that you can look at and see. We do have to talk about acid rain. That's part of the Utah State Core, and we'll talk a little bit more about it later. But you can see that acid rain is considered basically anything below 5 as far as the pH scale. The normal range for acid or for rain is between 5 and about 6.5, and that's because as water comes down through even the most clear, pristine skies, there are particles that the water captures and it becomes a little bit acidic. Then we get to baking soda, seawater, milk and magnesia, it's like Tums and ammonia and lye. Another pH scale here that we can look at for common substances, Coke, 2.6 on the acid scale, where battery acid is 1.0. So that's why Coke is really good at removing grease off of cement. Mountain Dew is even lower than Coke and actually works even better. Okay, so you can sort of see root beer up there at 6.6, it's almost neutral. Listerine, 5.45, and you can go all the way throughout. I mean, 7-Up, 4.3, Lye, which is what they make soap out of, is 13. Liquid plumber at 12. Tums at 10.5. Ammonia and detergent in water. So there's a lot of things that you can test. Make sure, again, that you don't use blood, feces, or urine to test those. Now, we're going to talk about some important equations. Besides the one we have used, there are several others that we're going to be using. The ones with a P in front, this is how I remember what to do with them. If it has a P in front, I'm going to do minus the log and then whatever the concentration is. pH plus pOH equals 14. Well, that makes sense if you look at the kW. Up at the top, it's 10 to the minus 14. So if I take the minus log of each of those and times them together, or add them together, I'm going to get 14. At the bottom, to find the concentrations, I'm going to go 10 to the minus pOH or 10 to the minus pH to go back and forth. Now, I do have a little handout here that helps, and it's something that I would use on my 3x5 card, but I gave you a big version of it, and I'll collect the extras when we get to this side. I'm not going to count. Oh, it's this. Okay, this is my lovely acid-base square that we can actually go through. Just because I want it to go forward, it doesn't want to. This is the acid-base square that I gave you. Of course, it's not colored, okay? But you can color it if you want to. And color code which way is what. But you'll notice that it's got all the equations on it. That's why I said it would be a good thing to put on your 3x5 card for the test. When I refer to H+, I'm really referring to H3O+, which is a hydronium ion. It's just a shortcut to say that it's a hydronium ion. Ben, please put that away. Thank you. Okay, so we're going to do some examples here with this. So get your calculator out. First thing we're going to do is just go back to our pH scale. We need to be able to look at a pH and tell me if it's acid, base, or neutral. So number 1, what is it? Everybody together. What is number 2?
Acid.
Good. 3.
Base.
Okay, good. So here's a warning. On the test, she might give you pOH. And it's the opposite. Okay, so you need to make sure you watch it. So if you know the pH scale, that's fine. If they give you pOH, just go 14 minus that number and you've got the pH.
So 3.5
Okay.
would be base and pOH?
Right. Okay, yes, so watch that. Okay, so now let's look at this again, this equation where it's minus the log of the concentration of hydrogen. If you're using my calculators, the solar ones, you actually have a button that has ln and log on it. You have to tap that button twice to get log. Okay, the first one that you tap will give you ln, and the second time you tap it will give you lno. It's right here, right underneath the second.
We have to tap it twice.
So you will go minus or negative the log. So let's try this one. Let's just put in our calculators. I know this is not in your notes. I want you to just practice. So type in minus, not negative, but minus the log. Minus, and then if you have my calculators, click log twice and make sure you get log. And then we don't really have to put in the 1, right? Because 1 times any number is that number. We can put 10 to the negative 10. And if you're using my calculators, it's the one that has the X and then the superscript box. Okay, what did you get? Should have got 10. Okay, let's try it again. This time with a little bit more complicated number. Let's try this number. Okay, so minus the log of 1.8 times 10 to the minus 5. Okay, got it? What'd you get? 4.74. On pH and pOH, we report to 2 after the decimal, always. Okay, so pH and pOH, 2 after the decimal. Do you notice any pattern here between the two that we just did? I'm going to show you a check so that when you're on the test, you can double check and make sure you're making the right answer choice. So 10, 10. Okay, 5, but this had a number here that wasn't 1, and I'm close to 5. Okay, so if I have a number before that's not 1 and I'm timesing by 10 to whatever, it'll be close to that number, but it won't be right on. Okay, so that's a quick check for being able to do that. Okay, now we're going to use this card that we have. Given a pH of 4.5, find pH, put your finger on it. Find pH on the square and put your finger on it. Okay, what we're going to do is we're going to find all the rest. Now I'm going to tell you a little trick that I do. I don't like to do across the bottom. And the reason why I don't like to do across the bottom is if I forget to put the parentheses around it, it screws up everything. So I like to go up and over because it's real easy to subtract 14 minus a number to get the other side. Okay, so I have a pH of 4.5. Acid or base? Acid, good. So we would say it's an acid, and then I would say, okay, if I want to find the pOH, what do I need to do going across the top? No, what do I need to do? Good, 14 subtract 4.5, so we get 9.5. Now, we have pH and pOH. Put your finger on both of them. How do I need to get to the bottom two? What do I need to do on both of them? To get H plus or to get OH minus, what do I need to do? 10 to the negative, pH or pOH. Well, I've got pOH here, I've got pH here, so I can really quickly go with the H plus, 10 to the minus 4.5. I cannot leave it like that. That is an unacceptable form. So I have to put it in my calculator and actually get the answer. And of course, it would be molarity. And I do the same thing with the pOH. I take that pOH, the minus 10 to the minus power of it, and I would get the concentration. Okay? All right, you got it? Grab out a piece of paper. This is not in your notes, or find a place on your notes where you can do it. I want you to start at this place on your square, and I want you to find the rest of it, the rest of the story. Tell me the concentration of hydrogen, the pH, the pOH. I've given you the OH concentration. Okay, give me the rest. Giving you 2 minutes. Go. I want you to find, I've given you this. I want you to find these three. Okay, 1 more minute. Got them down? Because she's awesome like that. So start with your concentration of hydrogen I gave you. Take minus the log of that. That'll give you pOH. Go up and over. It's easier to go up and over. Okay, another 30 seconds. Don't give me the answer up close. Okay, so here we go. Let's try it. I go up and over. You could go across the bottom, but like I said, that's where I see most of the mistakes for me and for every kid that tries to do it. So I go up and over, and then I don't make mistakes. So the first thing I need to do is take minus the log of that, and I get the pOH. Then, after I've got the pOH, I'm going to take 14 minus the pOH to get the pH. Then, I take 10 to the minus pH to get the concentration of hydrogen. Done. Okay, remember we really should put molar on the end of these, capital M. We're done. Okay, tell me, is this an acid, base, or neutral situation? Or,
So the pH equals 6.73?
yep. Okay, acid, base, or neutral? It's both?
Well, 6.73 is an acid and 7.
It's an acid, barely. Remember, we're looking at the pH.
Oh.
Got to look at the pH. So it's barely an acid, but it is an acid. Okay, only 7.0 is considered neutral. Okay, yes.
Miss Roberts told us when we did this lab that if it was like 6.93 or something, then it would be considered neutral.
It's, yeah. But usually we're in CE now. It's 7.0, nothing.
Yeah.
Okay, 7.00. All right. So here we go. 7.05 is considered base. Okay, so I want you to find, look, watch this. I want you to find the pH. So what I do when I'm using this, I'm going to borrow Juliana's, is I say, okay, what do I have? I have POH. Where am I going? pH. What do I need to do? Okay, I want you to tell me what the pHs each of these are, and if it's an acid or a base or neutral. Okay, I'm going to have people come up and pull the answers up here. Hi. In the sink.
Oh, sorry. Didn't see him there.
Yep. Yes. You're finding the pH of whatever I gave you, and then tell me acid, base, or neutral. Using the pH, yes. I think it was on your notes. Is it not on your notes? It's on your notes. Yeah, it's not the same number. It's like number 9. Right here. Oh, that's not nice. Yes. Yep. Bases are alkaline, acids are acidic. Okay, let's see who we want to do this up front now. Let's see, who have I not chosen? Braxton, have you been up? Okay, you get number 1. Okay. Let's see, who else have I not chosen? Elika, number 2. Sean, number 3. Okay, let's see if we agree. Number 1, thumbs up or thumbs down? Thumbs up, good. Number 2, thumbs up or thumbs down? Number 3. So number 3, I don't think it's right, but we'll.
I got it.
Is that what you got? Okay. All right, so what we're going to do is we're going to take minus the log of the 5.7 times 10 to the minus 4. Do that. So minus the log of parentheses 5.7 times 10 to the minus 14.
Wait, really? No? Because it's OH, you can't just go OH to 8 right?
Nope, you can go POH though. Okay, so somebody got an answer?
13.244.
No. So you're going to go minus the log of 5.7 times 10 to the minus 4. It should be close to 4. So the PLH is then 3.24. Then to find the pH, you go 14 minus that, which is basic. That's why I said go up and over. Go up and over.
Well, I just kind of wanted to learn how to do it the hard way, so I just did that.
Hey, what? You still get it. Right. I just find that more kids make mistakes going the other way. Okay, so let's go forward. Learning check. This means it's not in your notes. I want you to write it on another piece of paper. I'm giving you a pH of 8.3. I want you to give me everything else on there and tell me if it's acid, base, or neutral. Again. Again. I want to make sure you know these formulas backwards and forwards and forwards and backwards. You can do it. Come on, Ben. Yep, we are.
What? We're doing what?
Notes the whole time.
I thought she was finishing the whole thing.
That lab will be next time.
I thought she meant doing the whole thing.
Keep going. So you should be with this be able to do your pH home lab and finish it up.
So that would literally just be that.
So it's like the one we did at the very first. How'd we do?
I don't know, you did it.
Yes. Thumbs up. I got 2 thumbs up. 3 thumbs.
Wait, I'm confused. Can you help me real quick?
Uh-huh.
It says OH negative equals 10 to the negative P, so it would be 10 to the negative.
There shouldn't be a negative there. It's just 10 to the negative. Yeah, 10 to the negative. I thought you said negative 10.
So it'd be 10 to the negative what you get from the OH.
Yes. Okay, we have any problems here? We okay? No. No, we're not okay. Problems? No. Got it. I tend to fire questions out too fast, not let you respond.
Oh.
Okay, are we getting this box grid thing?
Yeah.
Understanding how to use it, going back and forth. Like I said, most kids, if you go up and over, whoa, they don't make as many mistakes. -9, -6.
Oh, never mind. That's from when
You just put it in the calculator. What?
Wait,
Got
why
it?
do they use the calculator though? I keep getting different things every time.
Okay, now I have one more thing and then. Oh, never mind, I found it.
Okay, so you just go 10, and then your button is here, and then you just go like minus 5.7, and then enter, which is 2. The log is if you got this and you're going this way.
Well, I did. If I do, it like gives me a whole different answer than everyone else, and I can't.
I don't know what you're doing. Yes, Ben.
Is, I don't get, so it says the OH is 10 to the negative 5.7 equals 2.00 times
So if you put that into your calculator, that's what you'll get.
10 to the negative 5.7, that's what I would have got.
No, that's what you put in your calculator. You can't leave it like that because that's not a correct answer.
Wait, so
So you put 10 to the minus 5.7 in and you get 1.9999 whatever. So it goes to 2.0. Okay, let's go forward or we're not going to make it through. Okay, so general reaction for acid and bases is this. It gives us a hydrogen ion. We have used this equation a lot. This is our dilution equation. C1V1 equals C2V2. It can be M1V1 equals M2V2. It can be MAVA equals MBVB, okay, for titration. But this is our dilution equation. It works really well, okay, especially if we've got an acid and a base that are 1-to-1, meaning one hydrogen to one hydroxide. If not, we've got to use the stoichiometric way, where we take molarity times liters gives us moles, get a balanced equation, go from moles to moles, and then divide it by liters to get back in molarity. That takes longer. So in this, you need to be prepared to make something like this. It's a dilution equation. So we're going to use M1V1 equals M2V2. So plugging in, we're solving for V2, M1V1 divided by M2. Plug in 0.500 molar times 750 milliliters divided by 6.00 molar. Molar cancels. What do we get? 62.5. Awesome. Okay, now it asks you to explain how to prepare it. I'm going to go over this again. We would get a volumetric flask that read 750.00 milliliters. So that is step 1. Step 2, and I'm a visual person, so I'm doing it as pictures. If you want to write it in words, that's fine. Step 2 would be to fill about 3/4 full with distilled water. Step 3 would be to put this much of 6.00 molar H2SO4 into the volumetric flask. Step 4, let's try that again, 4 would be to swirl it. That's my shortcut version to say swirl it. Step 5 would be to again take distilled water and add till the bottom of the meniscus hits that line. Okay, so you need to be able to explain what you're doing in a titration or in a dilution. Okay? Yes?
Well, I'm a little confused. When you are titrating, what are you doing? You're dripping something into it and you're swirling it until it turns into fluid.
You're trying to get the acid and the base to be equalized.
Oh.
Okay? All right, so let's go forward. Oops, I forgot that was already there. And then explain it. Okay, how many remember the solubility rules? We did them around Thanksgiving last time. I know. Okay, NAGSAG, does that help you remember?
Yeah.
Okay, what does NAGSAG mean? Nitrates, ammonium, and group 1 metals are soluble. SAG, sulfates, acetates, and group 17 metals are soluble. Okay, there were exceptions to the rule. Does anybody remember what they are? Castrol bear for sulfates, so calcium, strontium, and barium with sulfates are not soluble. And then it's a girl thing. PMS. Okay, so lead, silver, and mercury are not soluble with chlorine or group 17 metals. Okay, group 17 metals. Okay, so we're going to be using that. We need to remember that. I'll put this video up on Canvas if you need to go back and review it. We're going to be doing molecular ionic and net ionic equations. Ben, put it away or it's mine. Second warning. Okay. Well, when they're not paying attention, that's when I get ornery. Okay, so we're going to take hydrochloric acid, which is what? HCl. Good. Plus strontium hydroxide. Strontium is in the second column. It has 2 hydroxides with it. Both of these, one of these is a strong acid, one is a strong base. Because of that, they're going to both be AQ, meaning they'll dissolve into ions right away when hit with water. We're going to do the basic forward reaction, double displacement, OI, outsides and insides. So outside, we make water. I put it last. And inside, we make a salt, which is strontium chloride. Strontium, again, having a +2 charge. Chlorine have a -1, so we need 2 of them. Chlorine was one of our rules. It was group 17, right? And it's not part of PMS, so this is also going to be aqueous. Anytime we have water, it is in a state of liquid.
But I've seen it.
Or solid or gas. Okay, but it will never be aqueous. Okay, so now we just go and balance the equation by putting a 2 here and a 2 here. Okay, to get to the next point, which is an ionic equation, anything that's aqueous, I break back down into its ions. So this would break down into 2H plus AQ. Remember, anytime it has a charge, it's going to be AQ, or cute little ion, plus 2Cl minus AQ. This one would break down into strontium plus 2AQ plus 2OH minus AQ. Come on to this other side here. We get strontium, Sr plus 2AQ plus 2 chlorines, Cl minus AQ plus 2 waters that are liquid. That one does not split. Okay, what do you see that is the same on both sides? What is exactly the same? Has the same charge, same number? The chlorine, okay. Is there anything else? Strontium, good. These are known as, good, spectator ions. Okay, so now we're going to write our net ionic equation, which brings everything else down. So we would have 2H plus AQ plus 2OH minus AQ gives 2H2O liquid. But this is not the right answer. What do I need to do? Why isn't it the right answer? It is balanced, but they all have 2's in front of them. Simplify it down, and we divide both sides by 2, and we get H plus AQ plus OH minus AQ gives me water as a liquid. Okay? Okay, let's go to the next one. I'll do arrows. Okay, we got it? Sure. Okay, let's do the next one. Calcium. Calcium is what? Ca. What state is calcium in? It is not.
Solid.
It's a solid. It's a metal. So when you have a metal, think solid. So it's a solid plus water, H2O, which is a liquid, gives me what? So water usually breaks up into what and what? Not quite that far. OH and H. So what side is oxygen going to, or calcium going to go to? Who's it going to combine with? OH. So I'm going to get calcium hydroxide. There, calcium is a +2, so we need 2 of them. And this is a strong base. Because it's a strong base, it's AQ. Plus, what else do I get left over?
H.
And H is part of Braun-Hifkel, or the diatomics. So we get H2, and that's a gas. Is it balanced?
Yeah.
It's not. We need to put a 2 right here, and then it will be balanced. Okay, so we're going to do the net ionic equation. There's only one thing that's aqueous, only one thing that will split, and it's right there. So we write the rest as they are. Okay, is there anything side to side that is a spectator ion? No. So my net ionic is my ionic equation, and I'm done. Sneaky. Okay, yep. Going forward? Nope, nope, wait, nope, nope.
Wait, so since nothing is, there is no net ionic?
The net ionic is the ionic equation. Okay, going forward. All right, so this is practice here. I don't know if this is in your notes or not. Let me know.
Yeah, it is.
Okay, I want you to practice the first one and the second one. I'll put the answers up every once in a while in a few seconds here. The first one you're going to do M1V1 equals M2V2 or C1V1 equals C2V2. On the second one, you're going to write your equation. Okay, so take a second and do it. Nitric acid's HNO3. Nitric came from nitrate and hydrogen.
So we choose which one to do, one or two, or
You need to do both.
You don't have an option. That's nice.
No option. Come on. So you need to figure out how much you need to measure out and then tell me how to make it. I went through that with you already.
Oh, balls.
Oh.
I
Yes.
reversed it. I want to.
I'm here to torture you, Lexi. I'm just here to torture you.
is it CO3 carbonate?
CO3 is carbonate.
And what's the charge?
-2, but why have you got carbonate? Why do you have carbonate?
It's on in question 2.
Question 2 is nitric acid and calcium oxide.
Part B. Question.
Oh, part B. Okay. HNO3.
So charge, carbonate has a charge of -2 with -3. -3.
Are you okay, Ben?
He's having a twitch. Oh. CaO. You're thinking calcium hydroxide. This is just oxide.
Where's fluoride?
Cl, chlorine.
Oh, there it is. That's a terrible.
No, it's not. Perfect.
CaCl.
Okay, how are we doing? Everybody got the molecular equation?
So it'd be HCO3, which would be an acid,
Whoops.
carbonic acid.
Wait, can you show the answer? Yes! I didn't do it wrong.
Okay, how do we do?
I mean, I didn't get to number 2, but...
The spectator ions at number 2, I'm going to use green this time, were nitrate and calcium. So calcium and nitrate dropped out.
Stuck in my head.
You are living dangerously, boy. You don't want your phone for the weekend, huh?
You should see him in choir. He lives dangerously in choir, too.
I am. I can hand it right to an admin. Yep. Okay, going forward, it is true. Okay, ready? All right, so on this next one, go back. I want you to go ahead and start on B. We'll show the answers in a minute. So go ahead and do B.
So,
I'll even help you with the first part of the equation because carbonic acid, which is H2CO3, breaks down into water and carbon dioxide quickly. So we usually never write carbonic acid, which is H2CO3,
why wouldn't you, right?
because it breaks down immediately to carbon dioxide and water. Nope, you need to know it. Remember I told you the way to remember it from the periodic table? The 6 strong acids were HNO3, H2SO4, HClO4. So that's my oxy acids, that's the swoop. Then I started HCl, HBrHI, those are my binary acids. So there's 6 strong acids. On the other side of the periodic table, in the metals, we start with lithium, sodium, and potassium hydroxide, slide over, calcium, strontium, barium hydroxide, where you'd use 2 hydroxide. So that's a tetris pattern. Okay, so going forward here, you should have written the ionic equation like this. This goes on and on and on. What are the spectator ions?
I don't know. There's like 5,000.
What's the same on both sides?
Chlorine.
Chlorine is good. So we got chlorine and calcium. These are our spectator ions. They drop out for the main. So anything that's the same on both sides, it has to be exactly the same, drops out. Okay?
I wish it was the whole thing. Wait, how come you only put the liquid gas in water? CO2?
The rest were aqueous, AQ.
Oh, so we just didn't.
So aqueous just means strong.
Aqueous just means it's dissolved in water. So our final equation would be this. Now, really, calcium carbonate is chalk, so I should have done that as a solid, but we'll take it as being dissolved in water because you can dissolve chalk in water.
How would they ask these questions?
Okay.
What were the questions?
Yeah, what are the spectator ions? What's your net ionic equation? So that's solubility rules, right? Is it a nitrate? Is it an acetate? Is it a group 1 metal? No. Is it a sulfate? No. Is it an ammonia? No. And is it a group 17 metal? No. So it's a solid.
No.
Okay, so let's talk about bases here for a minute. Property of bases, we have a neutralization reaction. A neutralization reaction is this. What?
Will that ever give you like a specific, like, is CO3
Soluble?
or
Acid or a base, yes. Okay, so here we have a strong acid, strong base, give me salt and water. Whose theory?
Lewis.
Nope.
The weird one.
whatever in the
Not Bronsted. No, not Bronsted. The other one.
Arrhenius. It's Arrhenius. Okay. All right. So, for instance, when we take nitric acid and sodium hydroxide, our molecular equation would be this. Okay. So we're on to the next thing here. So write the molecular equation down. Now, looking at each of them, HNO3 is what? Strong acid, right? So is it what phase is it going to be in? Aqueous. NaAgNO, or try NaNO. Let's try that again. NaOH is what? Strong base. So it's part of the tetra, so it's going to be AQ. What about NaNO3? Nag, nitrate. It's AQ. It is a salt. And water is a liquid.
So salts are usually get the AQ.
Usually, but you got to follow NAGSAG. Okay? All right, so write the ionic equation. Break it down. We're going to keep doing this till you guys get it. Come on.
Okay, so Na are going to be on the same on both sides.
Mm-hmm.
And NO3.
So we just went through that. That's the solubility rules. So this was N of NAGSAG. This was a strong base. So because it's a strong base and this was a strong acid, they're going to be aqueous. The minute they hit water, the definition of strong means they go to their ions. Okay? NaNO3, that was both group 1 metal and nitrate, so very soluble. And then water is always liquid. So did you get this?
Well, I didn't really have a lot of.
That's the ionic equation?
That's the ionic equation. So what are my spectators?
H.
NO3 and Na, good. Those are my spectators. So I cut those out and I write my ionic equation. Net ionic equation, write it down. Write my net ionic equation down. Are you noticing anything about the net ionic equation? For an acid and base, it always makes water with a strong acid and a strong base. Oh! Yep, it always makes water. Okay, if it's not a strong acid and strong base, then you'll have other things that happen. If you end up with a salt that is insoluble, then you'll also have another thingy there. But it will always make water for sure. Okay? All right, going forward. Oh, wait. Yeah, we're almost done with today.
What time is it? The end of the day.
Okay, so here's another one, sulfuric acid. Let's take it, break it down.
I just ate so might be sulfate.
Uh-huh.
Yes.
Okay, I gave you the equation. Break it down to ionic and net ionic. Remember, you got to use solubility rules. If it's a strong acid or strong base, it will be AQ. No, you will need to write it.
SO4 and H2. I mean, those are our, that's the thing we don't include in the ionic H2s.
Oh boy.
And that would make, yes.
Okay, so we have this H2SO4 is a strong acid, so it's going to be AQ. KOH is a strong acid. It's going to be AQ. K2SO4 is on SAG, sulfate, so it's going to be AQ. And then water is a liquid. Since they're all AQ besides water, I could jump right to my net ionic equation, which would be what? H plus OH minus yields water. What are my spectators?
Wait, isn't H plus is a spectator because it's H2 and H2?
No, no.
Because you can't separate those two.
They have to be exact same side to side. Yeah, I know. It should have a 2 here.
I just forgot.
And it should have a 2 here. So you'll have a 2 here and a 2 here. I missed a couple of them. But when we balance it out, we'll get down to where it's just H plus yields this. So what are my spectators? SO4 and K plus, because they're exactly the same on both sides. Okay? Now you can look over other ones that we've been doing. So, we okay? Okay, let's talk a little bit again about what's going on. Next time, you need to have read this acidity lab so you know what's going on. You need to have the pre-lab done. You need to have the procedure written. You need to do a quick titration and a pH with a pH meter for each of the acids. You need to look and see exactly what you're doing for testing the indicators. You want to do that fast at the very first. Be done. Okay? Then, that's Tuesday. Thursday, lab notebook is due and we're finishing the lecture. Okay, so we're finishing the lecture, lab notebook is due. Don't come thinking you're going to work on lab notebook during class. You won't have time. If you're going to miss class for some reason on Tuesday, you need to be here Wednesday during tutorial to, nope. If you're going to miss Wednesday next week, or Tuesday next week, then you've got to come Thursday during tutorial.
Is there going to be tutorial Thursday?
Oh, yes, it is, because it's last week of the term. Okay, then we're going to go into the next week. You'll have your buffer lab that you do the first day that we come back in fourth term. And then we're going to do, if we have any more lecture to do, we'll finish that up. That last day is a cleanup. And then we're on to the test. Okay? All right. You should be working on sapling, guys. No. Last day of the test, 28th. No, it'll be next term.
That means we're here.
Except for lab notebook.